Good morning, Pathophys. Second part of Chapter 9 lecture today, we're just going to be covering one topic, and that's going to be synapses. I'm sure you all heard, it is Tuesday morning, 21st of April right now, as I'm filming this, and I'm sure you all heard about the governor. And closing school for the rest of the year. You guys have 3 weeks left. It's very sad for me to, as I'm doing this, thinking that I'm not going to be able to interact with you guys personally as a group, as I was really enjoying the experience this year with you guys. But at the same time, I'm going to do the best I can to give you all the material that you would have gotten regardless. Not going to give you any busy work, a couple assessments, a couple projects, and just keep it going that way for the next 3 weeks or so, and then I'll keep you posted. I'll probably put a schedule up for the remainder of the year, beginning of next week. So, with that said, I don't want to spend too much time talking to you about this, but this is an important concept, one that really, if you understand this, it helps you understand how a lot of diseases of the nervous system can affect the body. What is a synapse? A synapse is nothing. It's a silly answer. It almost sounds like a smart aleck answer, but a synapse is nothing. It's a gap. It's a gap between adjacent neurons. So once we figure that out, that your dendrites don't literally connect. So you have two neurons that are lined almost up, and they're almost touching, as I'm using my fingers here to illustrate, but they don't quite touch. They don't quite interact with each other. And that begs the question itself, and it's one that I often ask the juniors, like, okay, we figured out what a synapse is. It's a gap between adjacent neurons. Why? Why is it there? Why not just make a direct connection? Why put a cut in the wire, so to speak? And the answers, there are a number of answers, but the ones that make it probably easier to understand, it's kind of like a switch. It gives the body the ability to turn off nerve impulses, to control the flow, the movement of nerve impulses from one point in the body to another. So you have that little spot. Secondly, it allows for change in direction. We always draw these linear progressions of neurons, one neuron here, one neuron here, one neuron here, make it a straight line. In reality, especially in the brain, it looks like a three-dimensional spider web with neurons from multiple, or dendrites from multiple neurons interacting in multiple planes and directions. That's just how it works. So again, it allows us to switch directions, move from one point to another, and it serves as a switch to kind of turn things off when you need to. Now, understanding what a nerve impulse is and how it's generated. You generate a nerve impulse either in the central nervous system or coming from sense receptors. The sense receptors, obviously, are sensory neurons going back towards the brain central nervous system, and the motor neurons are leaving the central nervous system going out to effectors in the body. Effectors are things that are controlled by the nervous system, muscles and glands. Good examples to use there. So how do we get across them? If there's this gap there, it's not like a Hollywood movie where you see the car that's out of control and the sign that says bridge out, and you have a nerve impulse jumping from one dendrite to another. Now, actually, that's kind of what it does. But what literally happens as we get to that point in the synapse is that as the nerve impulse travels through, it's going to prompt the release of chemicals from the end of the dendrite called neurotransmitters, and you've probably heard of this before. Neurotransmitters do exactly what they say. They transmit nervous impulses. They form a bridge. They build a temporary bridge between the two dendrites, and that's their job. And this gap is, I believe, I don't have the numbers in front of me, something like 1/500,000th of an inch thick or deep. So again, I'll often ask the question as a bonus question on the test, how many synapses can you hold in an average human hand? And people start looking at their hands and figuring it out. The answer is there's no answer to that because a synapse is nothing. So we have to get across that. We use those neurotransmitters. There are a lot of different neurotransmitters, over 100 that the body uses to bridge these gaps. In the body for muscles, acetylcholine is probably the most common one. In the brain, we have ones like melatonin, dopamine, that allow nerve impulses to travel amongst the nervous tissue in the brain for communication there. And those, as I give you some of the diseases later in the chapter, are going to come into or play a tremendous role. Now, quick scenario before I wrap things up today. Let's say, for instance, you build a bridge, right? You have a nerve impulse traveling along. You build your chemical bridge with the neurotransmitters. You make that connection. Nerve impulse travels, right? So after it goes through, you have to close that gap, or you have to open that gap up again. You have to raise a drawbridge, so to speak. You can't have that constant movement through. Now, just a quick example. In the classroom, if you remember, in the front of the room, there's a picture of a soldier in the bridge position. He's laying on his back, in tremendous anguish. That is a picture of a soldier that has tetanus. Untreated tetanus, obviously. I think it's from the Spanish-American War, before we had antibiotics to treat tetanus or understood how to treat it. What happens in tetanus is that the bacterium, which is tetani, which makes sense because it's named after the tetanic contraction, which is a constant contraction of the muscles, what that bacterium does is it releases a toxin that does not allow this bridge to be broken down. So those nerve impulses continue to travel to their targets. So instead of just having one meaningful contraction, the muscle remains contracted because you're continuing to bombard the muscle with nerve impulses because you can't break down this bridge anymore. So there's actually chemicals in our body called neurotransmitter inhibitors that are going to break those down. So when you have a tetanus infection, you can't break the bridge. So the nerve impulse continues to travel. Now let's go to the other side of the equation, the other end of the spectrum. You decide to take a trip to South America because you're a frog enthusiast. You've probably seen some of the pictures of the colorful frogs before. I should have grabbed some before I started this lecture just so I could have shown you. So I was doing it. They're called Dendrobates or Xerobates. It's a genus of frog that are often called poison arrow frogs or poison dart frogs. They're tiny little things. They're highly colored, greens, reds, oranges, blues, yellows, very conspicuous, which if you think of something that could sit on your thumbnail, you probably don't want to be something snack in the rainforest. So you're sitting on a green leaf and you're colored red. You're basically saying, here I am. So why they do that? The coloration is a warning coloration. They possess a poison in their mucous membranes and the mucus coating on their bodies that is a strong and deadly poison for most organisms. So what happens with them, and why are we talking about frogs in reference to synapses? When you are infected with that poison, it inhibits the formation of neurotransmitters. That's what that poison does, literally what it does. So if you send a nerve impulse along the length of nerves, it can't cross the bridge, so to speak, because you can't build a bridge. It's not there. So the opposite end of the spectrum of the tetanus toxin, this one doesn't let you build neurotransmitter bridges at all or make that gap complete. You can't bridge the synapse. So what's the effect of that? Paralysis. We actually use derivatives of these same chemicals as anesthetics in the medical industry. So these are the things that you will be discussing when you talk about deadening pain, paralyzing people for surgeries, inhibiting gag reflexes. There's one called Pavilon that they spray in the back of the mouth when they're doing procedures where they're going to put a tube down the throat, like for endoscopies. Those are all things. You're inhibiting pain, you're inhibiting nerve impulse transmission, obviously at levels that are clinically safe. But the poison arrow frog doesn't worry about your safety. It just wants to get away from you and teach you a lesson if you end up surviving that. So the point of that being, again, what do people typically die from, or organisms die from that get a poison arrow toxin? They die from asphyxiation because they can't contract the muscles like their diaphragm and their intercostals that are going to help inflate their rib cage for respiration. So what is a synapse? It's a gap between adjacent neurons. What's its functionality? It's a stop gap. It's a switch. It allows for direction changes. How do we get across it? We use neurotransmitters. Have a great day. See you soon.